presenting to you power converter circuits and control design with Simscape. So hopefully we can share what we have knowledge for model-based design. So actually this one is part of our model-based design for electrification and renewable energies. So hopefully you are able to grasp the tools that we are able to show to you today, and and apply to your work in this case. So let me go through the agenda that we will be, yeah. So before we go for the agenda, I think my team will be doing an entry poll for today. So before we proceed, hopefully you are able to actually help us, to understand you better, to know you, so that, we can actually deliver something fruitful for you today. So yeah, so please get through with the entry poll as we go through the agenda. Yeah. Okay, so we'll wait for a while for you to be able to finish the entry poll. Okay. Yeah. Okay. Most are on the. Okay, some are more on the students or academic. Some are design engineers. Yeah. So most are new to the tool. Yeah. Okay, which type of converters? Mostly DC-DC inverters. Okay, and exploring. Okay. Okay, I think that's a very good poll. Yeah, so thank you very much for um, doing the entry poll and letting us understand you better and what you may want, or may we need to support you on this one. So for today, we'll have a more of a general sense of Simscape electrical, and how we can use it for modeling challenges in electrification and power electronics. We will use some of these electrical systems through model-based design workflow with MATLAB and Simulink tools, and then we'll discuss more of the Simscape overview and how these libraries or tools can be used for your power converter model development. And then at the same time, how do you do control systems in this case? So I'll be doing some demo also on how we can build a simple converter, and then adding a control system to it. So let me proceed with the webinar. So, of course, power electronics control systems design has its challenges, and these kinds of systems come with a lot of complex dynamics and interactions. Efficiency and stability of the system are very important, but also to give it another perspective is these systems should also be safe in operation, reliable, and it's a combination of actually selecting correct hardware also, and development of embedded systems that yields these results. So if you can see here, we are dealt with different types of in embedded software or embedded systems, particularly for control systems and power electronics. So we are dealing with primarily three sources of modeling. So one is power source, and then usually we have the power electronics, and then we are modeling also the software, the embedded software, the control systems that we are providing through this embedded system. And then we are also modeling the electric loads. So this is like a marriage of so many so many tools that we have. So it's an understanding of how we can actually understand the power quality in this case of the systems that we are actually doing, and then the how do we size certain components, for example, in this case, sizing or specifying the devices, compensating for energy storage, for example. In the case of battery, we can also use a Simscape battery for uh, um, parameter estimation or component degradation. In other cases, definitely for your embedded software, we are developing and tuning controllers and then with varying operating conditions. So these are just some topics that you may have questions in mind in actually developing your systems in this case. So so where do we find these challenges? And sometimes there are certain mistakes in certain when we are doing control codes. So where do we find it? So this is the common problem for anyone developing embedded software. So you need to test your code on a hardware system also. And in the moment, the truth and the reality is that you are dealing with a complex hardware and software system. So you want to actually test all the combined combinations of operations and then faults, but it's not practical and maybe expensive if we have a actual physical system, right? So we hope these mistakes are easy to find, but it's not. So maybe we are spending so much time and understanding the root cause and hoping, the there are we can do not hoping that these problems do not cause so much problems. So these are the challenges actually that we have in hardware and software integrations, where mistakes are first found during the stage where it's already difficult to troubleshoot. And yeah, so I what we want to actually always tell in with our customers is that how do we in this case Simulink and MATLAB be able to help us in this case. So with model-based design, so we're thinking it's a better way of power electronics control designs. So later on, we will show you how we can do a simple voltage controlled system in this case. We can also model using model-based design as an approach to using a system level or behavioral simulations. So at the start of a system design, we usually are starting on a system level. So depending on the simulations that you want to pursue, it depends on the fidelity that you want. So Simscape Electrical is also capable of actually providing these kinds of fidelity depending on your application or your simulation. So with model-based design, you are able to design with hardware and then software together, integration with the simulation, and then you are able to actually test the software using real-time hardware systems, and in this case more of real-time systems. And then with the Simulink model-based design workflow, and one important aspect is actually we are able to generate the code for production. So this is the case where we are able to develop without actually us engineers coding the the codes, or I mean the software to run the system, but through the design in Simulink or in Simulink control systems, we are able to actually generate an embedded code and reduce hand coding issues. So those are the problems that we want to actually avoid in this case of in your development of embedded software using for power conversion systems. So this is just an example of our customers that are using model-based design to reduce with which they are using actually for control, complex control systems, and actually reduce their time in their development. So this is an example of how our systems engineer needed to verify, for example, the design as early as possible. So I think this is the most important thing that we have, where we can use model-based design to actually verify your systems early on in design using models, because in use in previous times where we have a hardware already and then the software is still in development, so the issues that come out are already late in the project, so that it becomes expensive to solve the issues. So let's see how we can use model-based design to embrace actually this complexity in what we are doing with power converters or power electronics. So model-based design enables engineers to test the system um, even without the physical system not yet available. So this is an example of a wind turbine, right? So this wind turbine is actually can be modeled within Simulink itself using Simscape multi-body. In this case, we are able to actually develop a model even if the system or the actual hardware is not yet there. So in this case, we are also testing it safely, right? And not then there's no real cost with using model-based design in this case because there's no physical systems yet. And then with this, so actually it reduces complexity in a sense. If you see this wiring, it can be so the complexity of the systems is actually so vast that most of the systems that we have can be actually developed uh, within the model first, and then later on expanded into the real-time systems in this case. So let's see how model-based design can help you. So if you ask yourself, so what if we are able to actually verify your system's behavior through the entire process? So in this case, what if we can use models not only to design or simulate, but at the end of the system design, actually you can use these models during the lifetime of your system. So also call it like if you want it to be a digital twin of your system. So these are just certain examples where we are able to actually use the exact simulation models that we use during the design, and at the same time, at the end of during the production phase and through the life of the system, you can actually still use your models as a digital twin during the lifetime of your system. So this one is true model-based design. So how do we do a model-based design workflow? Number one, we do desktop simulations, right? So we do certain types of prototyping. In this case, we do a prototype of new functionalities, for example, and provide something with an existing code, for example. So these are just certain models that we can actually use for initially doing desktop simulations. And then we perform automated system tests. This is that would be able to us to actually um, determine certain conditions that may not be possible in testing in actual physical systems, right? So if the system is there, most of the time these physical systems or these models are very expensive, right? These hardware systems. So what we can do is actually do a simulation in the models within MATLAB and Simulink environment, so that it's feasible to actually do this testing. Examples are fault analysis, where we can actually determine certain faults in simulation rather than doing the faults in an actual hardware, which may actually destroy the hardware itself, right? So these are just some kind of examples that I can say where we can use this system test, which are not feasible outside of simulation. And then we can optimize certain parameters, for example, software or our models we want to actually update depending on the actual performance of the system. So these are just examples of how we can utilize this process of modeling. So in order to optimize these systems, we are able to actually simulate an almost similar category, similar situation as what we have with the actual physical model, physical system. So in this case, that's why it's always called the digital twin in this case. An example of this one is from ABB, where they are actually accelerating the application of control software for their power electronic controller. So the challenge is to actually be more efficient in the development process using MATLAB tools to accelerate the design and for high power converters. So the solution is to use MathWorks tools and validate their control algorithms. So these are more of model-based design application of the software and the process of for the controller. So the development time has been reduced and is able to actually implement the power controller within a short period of time. Another step that we need to do actually for model-based design is hardware in the loop testing. So hardware in the loop system, usually when we initially do our development or our model development, we start with model in the loop systems. This is just doing simulations within the MATLAB or Simulink level itself. But if we are doing safety critical systems, we are following the V model safety systems. So in this case, most of the time, we wanted to actually deploy our algorithms or implement these algorithms in an actual hardware. And then this actual hardware, maybe a PLC or maybe an electronic control unit, we are able to actually deploy um, a code which can be C, C++ in nature, it can be HDL, it can be PLC. So all these codes can be generated from Simulink and then deployed to a hardware and then actually doing hardware in the loop testing. So in this case, this is an example of what I was talking about for hardware in the loop, where we try to emulate the behavior of a physical system. In this case, for example, we have a plant model. A plant model is the system environment and the system hardware itself. So it can be, in this case, maybe if we're doing power electronics, then we have all these power electronic devices that we have, and then we have the load settings, or we have the load of the system loads connected to it. So this actually, this system itself can be actually placed in the speed goat device to be deployed. In this case, we are able to test it out and see how our software is actually behaving, in this case, for developing these control systems. So from here, actually, we can develop certain faults. So we can put faults within this model, and then we are able to actually test it out in the hardware in the loop, and then see how our embedded systems are behaving in this case. So we are also able to connect this virtual plant into any, as I said, it can be any of these devices, can be PLC or industrial PC for this matter. So there are different types of interfaces that can be used, OPC UA, EtherCAT, Ethernet with for PowerLink or CAN open. So these are our Profibus or Profinet. Those are the things that I think able to do controller design and hardware in the loop for this matter. And then finally, it can be used for production use. So this is where we are able to actually design and test the hardware independent functionality. In this case, both hardware and software we can actually test in this case. So there's a where MathWorks simulation environment, and then we are interfacing actually with vendor-specific IDEs, for example, or automation for hardware and vendor-specific systems. So this is one of the, you know, most of the systems that model-based design is actually helping you as the customer, you as the engineer, you as the developer of your control systems for power conversion and energy and electrification. So these are the steps that we usually do in this case. And then we are able to actually debug real-time algorithms directly from Simulink. So this is how we are able to actually run an algorithm. And then if we see a problem, a bug in this case, then we are able to actually immediately change certain algorithms within Simulink itself to be deployed in this sense. So an example of this is how Microsemi, for example, did a real-time simulation testing for power electronics for electric aircraft. So in this case, we are able to actually, they are able to actually complete a power electrical control unit, which consists of PWM control, data conversion, communications with the external devices, and running a permanent magnet synchronous mode PMSM system. So these are just examples of how we are actually developing hardware in the loop systems to be connected to your controllers and then for testing purposes. Then finally, once you have completed your design, usually the next step would be to use your system for virtual commissioning, for example, where you use digital twin for model-based design, for example, health monitoring of your system. In this case, the main systems that you have can be used for the models that you have can be used for monitoring your existing physical hardware assets. In this case, we reduce errors in the field data and then train operators for these new systems. So these are just some applications that we can use for this matter. So let me go through a little bit for the Simscape electrical in this case. Let me show you how we actually do different types of modeling systems, in this case, modeling dynamic systems. So I think if you have attended several of our webinars, we have always uh, telling about model-based design and how Simulink and Simscape is able to actually help you to develop models. So there are in this case for model-based design, there are three types of modeling principles that we can show you: white box modeling, uh, and then gray box modeling, and then black box modeling. In this case, for white box, for example, we know it's what we call first principles models. It's because we already know the system's equations for um, your plant or your system model. In this case, we usually use Simulink or Simscape, where we are in Simulink. Maybe you have system equations that you have, and then you want it to port it in to Simulink itself, then you can actually use Simulink. Simscape is much more of the physical modeling, where, for example, you have motors or semiconductors, switches, and all other mechanical, for example, mechanical systems, multi-body systems, fluids, and thermal. You can actually use a Simscape in this case. But most of the time, when we start with our modeling, those models that we have at the start may not be representative of what is the actual systems. So most of the time we need to parameter tune these models. So what we do is we use a Simulink design optimization to put much more closer the parameters that we have initially with our first principle systems. So in this case, we estimate the design we optimize from an actual system data, and then we actually compare the actual data to existing model, and then this system model can be actually optimized so that it can be almost the same condition. So in this case, we are able to actually change the parameters of our model, and then we are able to use this one to actually duplicate or make it as a digital twin in this case. Then the other one is more of black box. So in this case, maybe the system is too complicated. We don't have system equations for this. Most of the time, we use system identification to develop our models. So from system identification, we have input data, and then we have an output data from the actual measurements of the system itself. And then from there, MATLAB and Simulink will be able to help you using system identification to actually calculate the system equation for your system. And then this one, you will use all of these tools you are actually able to use for your control system development. So that's how I am correlating power electronic conversion systems, and then adding it with the control system so that you are able to actually fully develop a whole aspect system development in this case if you are doing embedded systems for power conversion. Today we'll more focus on Simscape. For this matter is much more of Simscape electrical. So let's just have an overview. So Simscape enables us for physical modeling. So in this case, most of the time that we have, instead of having all these equations, physics equations into Simulink, it's much better to actually place all the system's equation in physical components and models or libraries, which are much more easier for users to actually use it to develop their models. So in this case, I'm showing a motor model. So instead of developing it using certain equations, so you're actually using componentized systems and then put it as a whole system for a motor in this case. So this is the system equations, and then you can actually these systems equations are actually placed within the Simscape library itself, so that you don't really have to think about the system equations or component equations, but you can actually just connect it to each one of them. So Simscape helps you to develop control systems and test system level performance. So this is because we want that plant model or your system model to be modeled in within a virtual system, which is Simulink and Simscape, and then you are able to actually implement your control algorithms in Simulink, and then have a whole control system simulation. So that is, and then we are able to actually deploy these models in simulation environments such as hardware in the loop, or yeah, in Simscape, which because Simscape supports C code generation. So this whole model can be code generated also and then deployed to maybe real-time systems, and then that's where you can actually simulate your control systems within real-time application. So these are just some what you can do with Simscape. So, particularly for Simscape and Simscape Electrical, here are some of the components that actually you can use for, in this case, for Simscape Electrical and your development for power electronics in this case. So usually with power electronics, power conversion systems, so we definitely need semiconductors, which are switching, for example, or signal amplification. So we use the common MOSFETs or IGBT or SiC behaviors. What is really very good is that you're not only actually modeling the actual element or component itself, but you are also putting up thermal effects in this case, or heat transfer environments for this. For example, in this case, what I'm showing is as an example is a N-channel MOSFET in this case. So you are also able to actually develop certain simulations with thermal effects, so that if you are doing in a system itself, right, you are not only doing power conversion, but you are also checking thermals, and you have some thermal management systems within that control system of your power conversion. So in this case, you are able to actually develop certain control systems also for your thermal effects in this case. Within that, you are able to, easily measure power losses, for example, in this case. There's a lot of subset libraries, as I'm showing here. You are able to actually develop easily your systems in this case. So there's a lot of semiconductor capabilities for Simscape electricals. Not only that, we also have motor applications or translational or rotational actuators. So in this case, as I said, we don't really need to put up the equations for the motor, but actually, Simscape Electrical gives you already a, a developed library for the motors, which can be parameterized with data sheets, for example, or it can be data from an FEM software and then import it in Simulink in this case. At the same time, we are also doing thermal effects for these systems. So we are also checking temperature behaviors, for example, or heat transfer to these systems. In this case, motors, and then some switching effects if you are using some kind of code. Conversion, power conversions in this case. So these are just examples of how we are able to actually utilize Simscape Electrical to develop our motor plant models in this case. Simscape Electrical also have sensors. It can do modeling for electronic, thermal, mechanical sensors, which are analog or digital and can be parameterized in this case. So there are also we can also use sensor test effects of sensor damage, for example. So in this case, you are able to check sensor failures on a system. So that's why if Simscape Electrical has this functionality to actually um, enable or check faults within your system, so that you don't really have to do it on the physical hardware that you have, and then check the embedded software or embedded system that you have designed, and if it's behaving correctly to your fault in your system faults. So you are able to actually use these systems sensors for your system's design. Another component are op amps or logic. These are behavioral models for fast simulation. So you don't really have to have the internals of the op amp, but you can actually use behavioral systems in this case to analyze large circuits. You are also able to perform high-level design without those nonlinear effects of the normal circuit operations. So these are much more of logical systems in this case. Definitely, Chipscape Electrical also support passive devices, which have non-linear and non-linear devices and enable us to operate in much more realistic behavior in this case. And then you are also able to check, in this case, component failures or on a system level to check system level performance. And then you can actually do fault analysis. So this is the advantage for Simscape electrical systems, where you are able to actually integrate faults within your simulation and check the behavior of your algorithms. If these faults are being detected, so that you can comply with system safety protocols that you are actually developing. So these are the examples of components that you can use for electrical Simscape electrical. Last but not the least, you can actually there's a wide range of components that you are able to use in power electronics, or I mean electrification systems, in this case, more of renewable energy, for example, when you're doing simulations for microgrids. So you have maybe generators or motors in your application, transformers, and Simscape Electrical is able to actually support you with single line or three-phase systems, power systems. So there's a special library for this kind of systems when you have the Simscape Electrical. So power lines and FACTs, definitely the converters, that what we are talking about today, and then electrical drives for your systems. So let me have a short demo for how we can actually use Simscape Electrical. For example, in this case, I wanted to develop uh, a system for like a buck controller, buck voltage control with the voltage control systems. So we'll do it step by step first. So we do a system level design in this case. So we'll just follow certain requirements, for example, in this case. So for example, we have input voltage of 24, V out of like this, 12 volts, and some PWM requirements in this case. So what I will use is actually a library that we already have. It's much more of like a system level design where it's not componentized, but let me show you this one. So in order to do that, we can access the libraries within the library browser in Simulink. So in this case, you can click it here, or you can actually use as a Simulink library browser. So in this case, so let me open up my Simulink browser. Okay, yeah. So, so this is the Simulink library browser. So today we will be discussing more of Simscape, and then Simscape Electrical, definitely. And then we will use certain components using this library. So later on, we will use a control. We will use a passive components, definitely, for example, for our loads. We will use semiconductors or converters. This one is much more like a model for semiconductors and converters. In this case, what I will show you later on. And then we can use the sources library, where, for example, we have a DC source or an AC source or a three-phase source. We can use these systems libraries for this in this case. So let me go through, like, for example, how do we want to actually implement, let's say, a buck converter, for example. So let me go through this converter library folder. So actually, you can see a lot of converter systems that you can actually readily use in this case. But for our example, we will be using this system, which is a buck converter in this case. So using the library browser is just click and drag for the tool itself. So in this case, you are able to actually click and drag that component and then actually put it within your Simulink environment. You can double click the device, and then you can actually change the parameters that you want for this buck converter. So your buck converter can be a non-synchronous or a synchronous one. But for this one example, I think I'll just maintain to non-synchronous. We'll just put a PS gate control. For this switch, you can actually select which kind of switch that you want. It can be this ideal switch, or it can be an IGBT MOSFET, thyristor, or an average switch. For this one, I'll use a MOSFET with a threshold of, let's say, 0.5. Let's say I'm just putting up certain values that I have initially, just to meet the requirements that we have. And then we have an LC filter. So that LC filter that we have, right, in the buck converter. So maybe let's have let's say a 3.7 millihenry millihenry of inductance, and let's say 10 micro of microfarad capacitance. So let's say we have these specifications in mind, and then that's the systems that we will have. So using the library again, we will need a load, for example, for this a converter. So let's place a passive device. In this case, yeah, so you can see there's a lot of passive devices that we can actually use, capacitor, all these things, constant power load, yeah, which you can actually use for your systems. So in this case, we just click and drag a resistor. So in this case, we will use this resistor as a load. You can actually use different types of load where it can be a potentiometer, for example, in this case. But for now, for simplicity's sake, we'll just use this resistor in this case. So let's say we have a 10 ohm resistor. So we'll just change the value of this resistance. So 10 ohms. So, okay. Other ways to find components in Simulink is you can just actually double click within the Simulink environment and then search the 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 item that you want if you know already the name. In this case, for example, I want a voltage sensor for this one. So I just type on the search block, and then I'm able to actually find it here. So from here, so you can actually get the component without even actually using the Simulink library in this case. So let's do this. For example, we'll have this voltage sensor and maybe a current sensor. In this case, like this. And then we can actually interconnect all of this one. So for example, I have a voltage source here. So voltage source, in this case, like this. So we have this, sorry, this one, voltage source. Yeah. So we can have a voltage source here. So we can actually interconnect all these devices. So let's say we have a voltage source of a 24-volt one, and then interconnect it to the inputs itself. So we have this. And then for Simscape simulations, we need the solver configuration in this case. So this is a required interface for this. So let's connect the current meter to the load, just like how we do for normal simulations. We click and then drag the wire in this case. And then we wanted to have a viewer for our signals. So we will use a scope in this case to view our results. So we'll just connect it from the physical system to here, and then we have it here. So now we have the load, we have the converter already sized up, but what we need is actually a gate driver. So for the moment, I don't have a control system yet, so I will just have a PWM generator in this case to actually mimic a control for our converter. So in this case, I can actually interface it here and then connect it to the gate. And then I have a constant value, for example, of a duty cycle number. So for in this case, if we want the 24-volt input and a 24 output, 12-volt output, so how much is the duty cycle? Yeah, so 0.5, for example. So now we can actually simulate this system in this case. So let's say we have, let's say 2.5 milliseconds of simulation. So in this case, we have to actually change the parameters of the counter of the PWM settings. So I think we have a 100 microsecond PWM. So this is about 10 kilohertz, yeah, if I'm not mistaken, and then 5 microsecond sampling time. So in this case, we can check. So now we have a load current, which we can name as I load. and then we can have the V load voltage in this case. So let's try to actually simulate this system. So maybe let's try to do this. So I have the scope. I can put the grid. So we have two signals. In this case, let's try to simulate the system. Yeah, so what we have is actually the response of the voltage. In this case, we have an input, a 24-volt input, and then the output is actually about 12 volts. In this case, it is here. So in this case, we have a simulation results immediately in this case, where we used a converter system, buck converter system for this development. Maybe I can just show how you can actually put or place a control system. So with the control system, so you can actually place something like, in this case, this is your buck converter. Then you can actually use a control system. So actually this DC voltage control is actually already available within the Simulink library itself, within the control system. So for example, you have, in this case, you want a converter control. So this is the one we used for this system. So there are readily available voltage controllers, for example, in this case, a DC-DC controller. But if you have other systems applications, you may actually use this one. But in a general control of a system, so what we can have is also a traditional one. For example, in this case, I have this one I have developed using a PID controller, for example. So from the system initially that we have developed, so we have this 0.5, this control system, I mean, converter block. And then I have introduced a zero point 0.5 duty cycle constant. But here I have placed a controller, a PID controller actually in this case, where I have placed yeah, a PI controller to be exact, and then I can actually simulate a controlled environment system in this case. So these are my values for P and KI. You can do with Simulink control design, you are actually able to tune these parameters to get your system. So maybe we can try to, so in this case, this example is actually using the PI controller. So maybe let's try to simulate this control. Maybe let's try. Yeah. Yeah. So if you see here, this is just the response from the B load input is 24 volts, and then the output is about 12 volts in this case. So this is the PWM um, generated from this controller. In this case, you are able to actually control your systems in this case. Okay, so I think that's the part of my demo for hopefully we will share these links to you. This is actually examples that are online in MathWorks already. So you can actually use these examples to develop your algorithms. Key takeaways for these applications is that Simscape Electrical bridges the gap from theoretical design and then hardware design, and you are able to actually integrate simulation of circuits and controls to catch design errors early in your design phase. Hopefully, this helps you to make a digital twin environment for your converter systems and do an optimization for your controls. And with this webinar, we are able to actually show you from end-to-end workflow from how you develop a model. And actually, later on, you are able to actually do hardware in the loop systems. So this is my part, but before I end our webinar, I just like to invite you, if you have you are able to access actually certain on-ramp trainings online in MATLAB. So this on-ramp are free, and you are able to access these simulations for Simscape Electrical. So you are able to actually, like for example, this one is a circuit simulation on ramp where this is a self-paced training. So you can actually do this training in MathWorks online itself, and then run so that you can have a practice for circuit simulation. And then there is also a power system simulation on ramp where you can actually develop certain types of applications. So these are more of three-phase systems, high power systems in this case. Yeah. So with this, I finish my webinar. I pass to Sharifa in this case. Yeah, thank you very much for your attention. Yeah.